All right, so linear approximations and differentials are they're very similar in terms of what they're doing. They're just described differently in terms of the actual equations. So here's the idea of a linear approximation. Suppose like I want to estimate what the square root of 4.01 is. Okay, suppose that's just something I would like to do. Now, just because it's close to 4, you may be like, well, that's about 2, right? But let's say we want to be a little bit more accurate around it. We want to be a little bit more precise around it, is we can use a tangent line to be a little bit more precise, to say like, well, it's a little more than 2, but how much more than 2 then it is? And let me demonstrate it by like giving you a graph of like what the tangent line is going to do and what we're going to ultimately be doing here. So suppose I have f of x equals square root of x, and I am trying to estimate a nearby value of like 2.1 here. So then what I want to do is I want to create a tangent line. Okay, so let's compute the equation of our tangent line. So let's say f of x is equal to the square root of x, and I want to do a tangent line at x equals 2. Now, why do I pick x equals 4? Why do I pick x equals 4? Because I am attempting to compute close to the square root of 4, right? Square root of 4 is 2. And I know we have a calculator, so you might be like, well, why don't we just use the calculator to do it? But there's a reason why. I mean, just to understand the application is, say, like, I want a tangent line, and that way I can give you a better estimate of what the square root of 4.01 is, okay? So how are we going to compute the tangent line? Remember, the way we do tangent line is we do y minus y0 is m times x minus x0. So we need a point and a slope. So what is our point here is going to be x equals 4, and y would equal 2. That's our point. So that's because that's for this function. When the x is 4, the y value is 2. So this is going to be y minus 2 is mx minus 4. Okay? So now m is the derivative at 4, right? It's the derivative at that particular point. So we're going to compute the derivative. So f prime of x, using our power rule, is going to give you 1 over 2 root x, or if you just know it, right, like the derivative of that. So this is x to the 1/2. Derivative is 1/2 x to the negative 1/2, which is where I get this guy here. So f prime at 4 is going to be 1 over 2 root 4, which is 1 over 2 times 2, which is 1 over 4. So that means our slope is 1/4. So that means our equation is 1/4 x minus 4 plus 2. Okay? So let's take a look at what we're going to do with that. Is we're going to say like, okay, so what's our equation here? It's going to be y equals 1/4 x minus 4 and then plus 2. And let's confirm that indeed looks like the tangent line. Looks like I did that correctly. So now what we're going to do is we're going to say, hey, maybe I can't compute the square root of 4.01 directly without a calculator, but I can plug in 4.01 into the line and say, let's look at the point. Let's see. Let's call this g of x just to make it a different line. And so I can compute g of let me put the point 4 comma g of 4 right there, and I can label it, and I can tell you the other side, that's 4, but I can then do 4.01 and g of 4.01, and I can get a slightly different number. And so let's plug that into the calculator. And that point, you can see this is 4. 4.01 is very, very close because the two lines, because the function and the tangent line look very close to each other, it's basically going to be about the same amount, right? So then I just say like, well, I'm going to plug in x equals 4.01 into my tangent line equation. And this I could do by hand without a calculator if I wanted to, right? This would be 0.01 plus 2. 1/4 of that's going to be 0.0025 plus 2, and I get 2.0025. So that is my estimate. This is an estimate of the square root of 4.01 because we simply just use that tangent line to do that approximation. So the tangent line is nice to approximate values that are close by. Okay, so that's the main idea. Now, let's compare this to the exact answer. Desmos can tell us what the exact answer is going to be. So you can see that what do we get if we do f of 4.01, or what is the square root? And you see on the calculator it tells us 2.002498. Very, very close. Almost the same. There is a difference, okay? Don't get me, this is an approximation. It's not exact, but it's very close. Right? And so we say this is a good enough approximation. And honestly, your calculator is approximating it because it doesn't know the exact thing. It just knows how to do an excellent approximation of the value here. Okay? And so that's the main idea of that tangent line. So what we're doing is we're saying, just to summarize, what we're doing is we're saying we have a function and I want to approximate, I know a value here, like I know a point here. Okay, or we call it a and f of a. And I want to estimate another value here, but instead of getting the exact value, we use a tangent line and then get this value instead up here by plugging into the line. Now there's a difference, there's a gap there, right? But it's not like super critical. Like it's pretty close in there. Okay? So that's the main idea of what we're trying to accomplish, is we're trying to say like, oh, there's a difference, but the tangent line is a close enough approximation. Now, how do we know if it's an over or underestimate? It has to do with whether or not the tangent line is above or below, but it has to do with the concavity. The second derivative tells us if it is an over or underestimate. Over or underestimate. Okay, so if the second derivative is negative, that means this curve is concave down, we're going to overestimate the value because our tangent line is going to be, the y value is going to be greater than the actual function. And if the second derivative is positive, then we say this is an underestimate, because what would happen in that case then, the function would be like concave, even if it was decreasing. It's not whether it's increasing or decreasing, the concavity. So even if you had concave like that, the tangent line is always below the function. So there's always going to be that gap that is where the y value is underneath the curve. So the estimate will be an underestimate. So that's how you can tell whether it's an over or underestimate. But the main idea is we're using the tangent line to approximate a value nearby. Okay. Now, there's another way to do this with differentials. It's a different way of describing what we did. So let me explain what we did before. And I'll do it with like a big function here. Like I'll try to, with a big graph. So we did a tangent line here. And I'm going to try to exaggerate how far away we were. But let's say we pick a tangent line like right here, okay? So this is the point we call, say, A, and then the y value here is f of A, okay? And then we picked another point here. We just said like it was the nearby point. We called it B, and we used f of B. And what we did is we did the equation of the tangent line here. Now another way to think about this is to think about that instead of calling this B, we call it A plus dx. Okay, where dx represents the distance from here to here. So like it's the spacing here. This spacing here is dx. And then we call this spacing here the difference in the y value dy, like how much higher it is the point. So we call it that distance there dy, and this is that f of a plus dx part, okay? That's that y value there. Now the slope, which is the derivative dy over dx, is the ratio of dy and dx here. So dy, we can treat it as like the spacing that we have from the original point to that thing. So let's talk about, let me give you an example here. Suppose we have the point 4, so this is, again, f of x equals the square root of x. So then we have the point 4,2, and we would like to estimate when x is equal to 4.01. So another way to describe what's happening here is we say like, okay, so this is 4, and then this is 2, right? Because this is the point 4, 2. And then we're going to say, what's the dx? Dx would be our distance. In this case, dx would be 0.01 because it's the spacing between here and here, the distance horizontally between where I want to estimate my value and where my actual value is. Okay, now what we do is we say, well, we have y equals square root of x, and then we write this notation. Dy dx equals 1 over 2 root x. And so then you can treat this guy like a fraction, dy over dx, as dy is equal to 1 over 2 root x dx. Now this is called a differential right here. This is a differential. Because you might be like, I thought this was just notation. It is notation, but the notation is there because it is a ratio of two values, the dy over the dx. It's a slope, right? So it's the change in y divided by the change in x. So I can move the dx up like that. Now, what does this tell us is dy is equal to 1 over, and if I plug in our point, okay, x is 4, so 2 root 4 times dx, and treat dx like a number, right? It's the spacing here, 0.01. This is 1/4 times 0.01, which is 0.0025. So what does dy represent? Dy represents the distance between here and here, between the two and the value I'm trying to approximate. So dy is this distance. So then your estimate for y, so the square root of 4.01 is about equal to y value plus the dy value, which is 2.0025. Okay, so we get the same thing, but we're describing it differently because the dy is kind of like this spacing here. It's kind of how much distance there is from, it's how much you're changing from that 2 value. The y was 2, and so the dy being 0.0025 means we go up 0.0025 to get to that point. Again, it's describing the same thing, but this is the real main idea around it. Is the differential is you take the derivative and then you move the dx up, and that solves that differential for you. So the next thing is a lot of examples using this kind of either idea of a linear approximation or a differential to estimate either a change or estimating a value. But they're both two sides of the same thing. There are ways for you to estimate the change or estimate a value of a function based on the context of what you're being asked. So we'll see a lot more examples of that here. So the next thing we're going to be looking at is linear approximation and differentials. And both are similar in terms of the execution, but just the concepts are they're both very similar in the idea. And the idea is that we're going to use a linear approximation to estimate a value, to say, like, I'm going to look at it as a straight line near a point that I know. And we can either describe it as a differential or as a linear approximation. So as an example, say I'm trying to estimate the value of a function, say around here. But I only know the derivatives and stuff about here. Well, I can use a linear approximation to estimate that value, say here. Or I can look at it similarly as a differential, like a change in x, a dx, and a dy. And so that's the basic idea of it. That's why they're kind of very related and very similar ideas. So as an example, given p of 0 is negative 67, and I believe there should be a prime there. Let me just double check and p, yeah, one of these should say probably p prime is 5. So say it's like this. This is supposed to be the derivative. So say I know the value of the function and the value of the derivative. Approximate p 110. So there's two ways you can do this. I'm going to do this both as a linear approximation and as a differential, just to show you this. The first thing we do is we say, well, I can create a tangent line at this point. And so it'd be y minus y naught is equal to m x minus x naught, right? That's the slope point form I would use for any equation. Well, my point is 100 negative 67. So it'd be y minus negative 67 is equal to m times x minus 100. And then we would say the slope is the derivative at that point, so it's 5. Okay, so this would be y plus 67 is equal to 5 x minus 100. Or we would say y is equal to 5 times x minus 100 minus 67. Okay. And so if I were to use a linear approximation, I would say y of 110, for example. I plug in 110 here. It would be 5 times 110 minus 100 minus 67. And I would get 5 times 10, that's 50, minus 67. And that's equal to negative 17, right? Okay, so that's the way we do it with linear approximation. Differentials is very similar, but differentials is just like thinking about it a little differently. We're basically saying, okay, we're going from the point 100 to 110. My change in x is 10, okay? What is my change in y equal to? Well, my change in y would be like this derivative, p prime of 100, is really equal to the dy dx. It's the slope, right? It's the change in y over the change in x. So my dy, my change in y, which is what it would be equal p time the derivative of 100 times dx. And the way we would say this, if my change in x, my dx, is 10, and this is the derivative is 5. If my change in x is 10, my change in y is going to be 50. 50 times 10 would be, so 50 would be equal to 5 times 10. And so since I start at negative 67 here, negative 67, that means I go up by 50. So I add 50 to this, and I end up with negative 17, and that's where I'm at. So that's the differential approach to it. And I'm going to use interchanging between the things. I think the differential is a better intuitive understanding of what's happening. Linear approximation is fine. That's actually what they'll do on the AP Calculus exam. But I think thinking of them as differentials is also useful, because it's useful if you study physics or other more complicated calculus down the line. So for number 2, knowing that f of 1 is 25 and f prime at 10 equals 5, which approximation using linear is likely to be most accurate? Oh, this should be f of 10, by the way, is equal to 25. Which is likely to be more accurate, and explain your reasoning. Well, you see, the tangent line approximation is only really good when it's better the closer it is to this point. Because if I'm very far away, like if I were to approximate this value and I use this tangent line is good for approximating nearby here, but you see, the further I go away in the x direction, the bigger the error is going to be. So that's why f of 10 plus 1 is the most accurate, because I'm closer to 10, and so this tangent line approximation, while introducing some error, is a small amount of error compared to when I'm very far away from there. For like f of 20, where I'm like much further away. Okay. So given h of 0 is 17, h of 2 is 29, approximate h prime of 2. This is approximating a derivative from 2 points. And so this is kind of the reverse idea, is to say, well, if I know h of 0 is 17 and h of 2 is 29, and I wanted to estimate this derivative here, like the tangent line slope, I can estimate it with the secant line slope. It's not perfect, but it's pretty close. So I would say h prime of 2, you could say approximately equal to h of 2 minus h of 0 over 2 minus 0. Like I said, it's the only slope that's a good approximation. And again, we're just simply using a linear approximation to approximate this value. So this would be 29 minus 17 over 2. That is 12 over 2, and that's equal to 6. Okay. 4. Let v of t measure the velocity in feet per second of a car moving in a straight line t seconds after starting. What are the units of v prime of t? This is a conceptual question. So v of t is feet per second. V prime is going to be the derivative, so it's really dv dt. It's the change in velocity over the change in time. That's how we're going to think about this notation as differentials. It's the change in velocity over change in time. Change in velocity is feet per second. Change in time is second. So the units of this would be feet per second squared. Okay. Given that e to the 0 is equal to 1, approximate the value of e to the 0.1 using the tangent line of f of e to the x. Sorry, I guess when I copied it over, it's not like in the exponent very well, at x equals 0. Okay, so tangent line approximation, y minus y naught is equal to m, x minus x naught. So we're doing the point 0, 1, so it's y minus 1 is equal to m, x minus 0 because we're using this function at x equals 0. So x is 0. When e to the 0, I get 1, so the y value is 1. So y minus 1 is equal to mx. Well, the derivative of e to the x, f prime of x, which would be the slope of this tangent line, is e to the x, and f prime at 0 is also e to the 0 is equal to 1. So the slope is 1. So I have y minus 1 is equal to x, y is equal to x plus 1. And so e of 0.1, I would approximate it as 0.1, plugging in 0.1 for x plus 1, or it's about 1.1. Okay. Approximate this using a linear approximation around x equals 1,000. And the reason I do this is because, hey, I know what the cube root of 1,000 is. The cube root of 1,000 is equal to 10, right? Because 10 cubed is 1,000. So the function I'm using is f of x is equal to the cube root of x, and I'm approximating it around x equals 1,000. Now, so my point is 1,000, and the y value is 10. So it's y minus 10 is equal to m times x minus 1,000. So I just need to compute what the slope is. I do that by computing the derivative. Well, this is a cube root of x. That's x to the 1/3. The derivative would be 1/3 x to the negative 2/3, right? And then I'm going to compute the derivative at 1,000. So this is 1/3. I'm going to write this as 1 over x to the 2/3. So this is 1/3, 1 over 1,000 to the 2/3. And that's 1/3. Cube root of 1,000 is 10. 10 squared is 100. So it's 1 over 300. So the derivative is 1 over 300. So my equation is y minus 10 is equal to 1 over 300 x minus 1,000. Okay? And so then I can plug in 1,005. So I'm going to get y minus 10 is equal to 1 over 300 times 1,005 minus 1,000. That's 5. That's 5 over 300. So y would equal 10 plus 5 over 300, which is 10 plus 1 over 60, whatever that ends up being. You could calculate what a decimal of that is. Now we're going to use the differentials. So rather than doing a linear approximation, we're going to use differentials. This is basically the same idea. But here we're doing a differential of y is equal to, or f of x, well, we'll say y is equal to x squared. So my dy, the way I do the differentials in concept when I have an equation, is I just do the derivative, 2x dx, like this. Another way to think of it is I do dy dx is equal to 2x, like this. I'm just doing the derivative. And then I just move the dx up here. And so I'm going to say dy is equal to 2x dx. Okay. Another way you can do it is just say when I take the derivative or the differential, I'm going to call this dy. And when I do the differential of this, it's kind of like the derivative of x squared with a dx at the end. Okay. So I know 3 squared is equal to 9. So I want to know what the change is. When x changes by 0.1, what is the dy is? The change in y at 3 is x is 3, dx is 0.1, because I'm going from 3 to 3.1. X is changing from 3 to 3.1. So this is 6 or 0.6. And so that means my y, so if my x changes to 3.1, my y is going to, like adding dx here, I'm going to add dy to this side. My y is going to go plus 0.6, so 9.6. Okay. Same idea here. We're going to say, well, y is equal to x squared. So dy is equal to 2x dx. What's the nearest square that I know? 5 squared is 25. So that means my x is 5, my y is 25. And now I want to know when my x plus dx equals, in this case, it's going to be 5 minus 0.05. Right? So my dx is equal to negative 0.05. Because that's the change from 5. From 5... my change is to go to 4.95. That's to subtract 0.05. This equation will tell me what my dy is. It's 2x times negative 0.05, which is 2 times 5 times negative 0.05. This is 10 times negative 0.05, or negative 0.5. And so my y value, so if my x value decreases by 0.1, my y value is going to decrease by 0.5. So my estimate would be 24.5. And if I were to do the exact calculation of 4.95 squared, I would get the exact value is 24.5025. So you see, we're pretty close in our approximation here. Okay. Here I'm doing y is equal to the cube root of x. That's the function I'm approximating. And I'll note that the cube root of 27 is equal to 3. So I want to compute my differential, my dy, just taking the derivative. This is really x to the 1/3. By doing power rule, it's going to be 1/3 x to the negative 2/3 times dx here. So in this case, if my dx is -1, because my x is 27 and my y is 3, and my new x, when I add my new x value, is 26, so I subtract 1, right? So that means my dx is equal to -1 in that case. My dy is going to be 1/3 27 to the negative 2/3 times -1. Okay, so 27, cube root of that is 3. 3 to the negative 2 is 1/9, so that's 1 over 27. Or 1 over 9 times 1 over 3 is 1 over 27 times -1. That's -1 over 27. And so my y value, my approximation, my x decreases by 1, my y is going to decrease by 1 over 27. That's 2 and 26 over 27ths. Okay. Similar here, y is equal to what? 4th root of x. Okay, and I know that the 4th root, the closest one is 64. The 4th root of 64 is equal to, no, wait, what is the 4th root of 64? Is that right? 4 times 4 times 4 is 64. 2 times 2, I don't know what the 4th root is. Okay, what's my nearest 4th root? 2 to the 4th is 16. 3 to the 4th is 81. I think this was a slight typo. I'm probably going to make this the cube root instead. I probably just typed that in wrong. So I'll make this the cube root. So we're going to do x to the 1/3. And the cube root of 64 is equal to 4. Right? So my x is equal to 4 and my y is equal to... my x is equal to 64, my y is equal to 4. That means my dx, the change from x to this value, is equal to 4. And so I need to compute what dy is. It's 1/3 x to the negative 2/3 dx. And so if dx is 4, my dy is 1/3. My x value is 64 to the negative 2/3 times my dx, which is 4. So that's 1/3. Cube root of 64 is 4. And 4 to the negative 2 is 1 over 4 squared times 4. And so this is, one of these cancels, is 1/12. Okay. Yeah. So that means my y is going to increase by 1/12. So my y would be 4 and 1/12. Okay. So that's how you think of the dx's. They're changes in x and changes in y, right? So you're always thinking, in this scenario, my x is 64, my dx is 4, and so my x is going from 64 to 68. My y is 4, my dy was 1/12, and so my y is going from 4 to 4 and 1/12. So we're thinking about the change in x causing a change in y. Okay. Here we're doing y is equal to sine of x is our approximation. And what's the nearest one that I know? Well, I know sine, what's close to... see, the problem with the number 2 is you got to think, like, you could think 0, but 0 is not that close to 2 in terms of radians. Like pi is 3.14, so you might want to start with, like, I don't know, pi over 2 maybe. But then you wouldn't have a difference. I guess I would just use 0. But 0 is not particularly close, so the approximation is not going to be that great. But my dy is going to be cosine x dx. Okay, and so my so if I do if I do sine of 0 is 0, right? And so my x value is 0, my y value is 0. My dx then, because I'm going from 0 to the value that I'm interested in, which is 2, my dx would be 2, and so my dy would be equal to cosine of 2 dx. Oh, sorry, cosine of 0 times the dx, which is 2. Cosine of 0 is 1, so we would say 2. So we would say sine of 2 is approximately equal to if I'm going to, my dy is 2, is approximately equal to 2. Now, this is actually a very poor approximation because the difference is so large. You probably did need to pick something a little closer because the way you want to think of your unit circle, you want to think of how close you are to 0 here. This is 0. Pi is like 3.1, right? So this is 3.1 over here. So, and then half of that would have been like 1.65. So 2 is somewhere like between here and here. Maybe even pi over 4 is the closest. Or 3 pi over 4 is probably the closest one. So if I were to approximate as 3 pi over 4, I would say, well, let's just see what 3 pi over 4 is. It's really equal to 2.36. Okay, so why don't we use that one instead? Because I know the 3 pi over 4 a little bit better, right? So for example, I know sine of 3 pi over 4 is equal to positive root 2 over 2. Okay. And so that's my x value. My dx would equal the value I'm interested in, 2 minus root 2 over 2. Okay. Or 2 minus, yeah, this, not root 2 over 2, 3 pi over 4, which I said was 2.36, so it's negative 0.36. So my dy would be cosine of 3 pi over 4, my x value, times dx, right, using this equation over here. And so this is cosine is negative root 2 over 2. My dx is negative 0.36. And so if I do that times negative root 2 over 2, I get this is 0.25. And so my approximation of sine of 2 would approximately equal to whatever the sine of at x was, right? Root 2 over 2, plus my dy value, which is 0.25, like this. Okay, so that would be my approximation. How about ln of 1.2? Well, I know ln of 1 is equal to 0, not approximately. So I know my equation is y equals ln of x. And so my differential dy is equal to the derivative of this, 1 over x times dx. Okay, so my x value is going to go from 1 to 1.2. So my dx is equal to 0.2, right? Because that's what I add to 1 to get to 1.2. And so my dy, my change in y, is going to be 1 over x. My x was 1 times 0.2. That's equal to 0.2. So my y value is going to go from 0 to 0.2 because I'm going to add dy to it. Yeah, so ln of 1.2 is approximately equal to 0.2. Okay. Oh, actually, yeah. So yeah, no, I did that right. Okay. Here we're just simply computing the differential. So we're going to do dy is going to be 2x dx plus 3 dx. What you have to think about is every time I have an x, I still gotta put a dx when I take the derivative. So it's going to be 2x plus 3 dx. That's my differential there. Here, dy, well, this is going to be 1/4 x to the negative 2, right? This is the way, because this is the 4 is in the denominator, so this is 1/4. So this derivative is going to be 1 over 4 times negative 2, just applying power rule, times dx. That's negative 1/2, 1 over x cubed dx. That's my differential. Here for dy, I'm going to do product rule. I'm going to do the first, which is x squared times the derivative of the second. The derivative e to the x is just e to the 3x, e to the anything. But then because the inside's not x, I got a chain rule. I'm going to multiply it by the derivative of the inside, which is 3. And then the derivative of this times e to the 3x. And then all of this is going to have dx times it, because that's how the differential rules work. Okay, dy. Here I'm going to do quotient rule. I'm going to do bottom, which is tan x plus 1, times the derivative of the top, which is 2, minus the top times the derivative of the bottom. Derivative of tangent is secant squared. Derivative of 1 is 0, divided by tan x plus 1 quantity squared dx. And I don't know. I don't think I can really simplify that a whole lot. So I'll just leave it like that. So this is really just practicing derivatives, just writing it a little different, writing with the dx on this side instead of down here. Okay. Because for all of these, you would basically say dy over dx, right, is equal to this. That's what the derivative is. I'm just simply moving the dx up there, right? That's all I'm doing. And so dy, I do product rule. I'm going to do the first, which is e to the x, times the derivative of sine x, which is cosine x, plus the derivative of e to the x, which is e to the x times sine x. And all of that gets multiplied by dx. Here, dy, derivative of this product rule here, I'm going to do x times the derivative of ln x, which is 1 over x, plus the derivative of x, which is 1 times ln x, minus the derivative of x, which is 1. So this is 1 plus ln x minus 1 is equal to ln x. And then I need to throw in a dx there, because there's a dx when I do it as a differential. A set of plastic spheres are made to be with a diameter of 1 centimeters. If the manufacturing process is accurate to 1 millimeters, what is the propagated error in the volume of the spheres? So this is kind of an application of differentials. You kind of think that I'm looking for the volume, right? And so the volume is equal to 4/3 pi r cubed. I want to relate the change in radius and how it changes the volume. So my differential is dv is 4/3 pi times 3r squared dr. So that's 4 pi r squared dr. And so this differential, I would need to know, well, so the radius is 0.5 centimeters. And my dr is the percent accuracy, is 1 millimeter. So we're going to make this point, in terms, I want to put everything in centimeters. 1 millimeter is 0.1 centimeters. So I'm going to get 4 pi times 0.5 squared times 0.1. I'm going to get 0.314 centimeters, which is 3.14 millimeters. So that means a 1 millimeter error in the radius will propagate to a larger area in the volume, because volume is proportional to r cubed. So a small error in radius makes a bigger error in the volume. Okay, that's how we do. You just use the differentials. That is basically what we're computing for the propagated error. Okay, so I have a cross-sectional area of a circular log. If the diameter, so cross-sectional error, that's what the area, I want the area. The area is pi r squared. If the diameter is measured 15 inches, accurate to 1/4. So my differential for the area is dA times pi. The derivative of r squared is 2r dr. So this is pi times 2 times the radius, which is 7.5 inches, and dr, which is 1/4 of an inch. Okay, so this is 2 pi times 7.5 divided by 4. I get 11.8 square inches squared is the propagated error. So even though I'm accurate to 1/4 of an inch, it makes a pretty large error in the area. 2 pi 7.5. Yeah, that's right. Okay, length of a wall is to be approximated. Yeah, sorry. Length of the wall is to be approximated. The angle theta shown is measured 85.2 degrees accurate to 1 degrees. Assume the triangle is formed. What is the measured length L of the wall? Well, so for part A, we just need to know, well, given a theta, how am I going to find this? And I can realize that, well, tangent of theta will give me L over 25. The L would be 25 tangent of theta. That's equal 25. The exact measure was 85.2 degrees. Right, so that's 25 tangent 85.2. I get 298 about feet. Okay, so that's part A. What is the propagated area? Well, here I'm going to have to use this error because the error is on theta, and I want to compute what the error on dl is. So the derivative is secant squared theta d theta would equal dl over 25. Just taking the derivative or the differential of both sides. And so dl would equal 25 secant squared theta d theta. That's 25 secant squared of the actual measurement, which was 85.2 degrees, times the d theta, which is 1 degree. Now, I think you need to be a little bit careful on here because you need to do all of these in radians technically. Okay, when you do these, not the trig, but this one needs to be in radians. So the one because that's these derivatives implicitly on all our trig functions. The trig functions are in radians when we're doing the derivative. So when I multiply by this d theta, this needs to be in radians. So this actually has to be 1 times pi divided by 180 degrees. Okay. And I can't do secant on calculator. I can do 1 divided by cosine 85.2 squared, and then times pi divided by 180. I get the error is 62.3 feet. Ooh, that's a huge error. Is that right? Let me see. Yeah. Looks right to me. 62.3 feet. That's a giant error. The percent error is 62.3 divided by 298. Because the actual measurement was 290, or our actual estimate is 298. So this is a pretty large error. That's 20.209, which is really 21% or so. Or 20.9%. Right. Okay.